Okay, thank you for the introduction. So in this work, we're looking at Cartesian sampling for MR thermometry. The main reason here is that the reconstruction here is very straightforward and fast, so Cartesian sampling is very well suited for real-time applications. These pulse sequences are also widely available, so it should lead to fast integration into the clinical workflow. In PRF thermometer, there are certain trade-offs that needs to be considered. So you obviously want a high precision in your measurement, so you can get this by using a long echo time, but this can result in long scan time. Sorry. You want a high sampling duty cycle because your precision is going to be proportional to the square root of the time that you actually spend sampling. So, but the trade-off here is that you can get large off-resonance effects. You also want to complete an accurate monitoring. So you want to image over a large field of view or a large volume, and you want high spatial resolution. But both of these things will take time. And then to minimize your off-resonance shift, you want a high bandwidth, but that will negatively affect your SNR and therefore also your precision. So what's currently done for brain treatment is a 2D GRE with a single slice and a single echo. So as you can see in this schematic of the readout, we have a very high sampling duty cycle to get a good precision, but that results in a low bandwidth and therefore large off-resonance effects. So one way to compensate for these off-resonance effects was presented on the previous symposium 2 years ago by Dr. Box-Polly. So you can take the long readout and split it up into multiple shorter ones. So you basically get a high bandwidth for each individual echo. You keep this total duty cycle pretty high, and you have the longer echoes, which if you combine them correctly, can help improve the precision. An alternative to this, so instead of reading the same line multiple times, you can do an echoplanar approach where you traverse k-space faster, so you can then trade that speed for a larger field of view. Each echo still has a high bandwidth, and so you get a small off-resonance effect, and depending on how long your echo train is, you can get a rather long TE. So in this work, we compare the current 2D single echo approach to the multi-echo, and also a 2D and a 3D EPI approach. So we did experiments on a Siemens scanner with a exablate neurosystem that we recently had delivered. All protocols used the clinical 1x2x3 resolution, and we evaluate the precision over 60 seconds of scan time. So initially we did a comparison between the body coil, which is usually used for these brain treatments, to a setup where we put one flex coil posteriorly and one anteriorly on the volunteer, as we can see in the figure here. So we saw about a 35 to 70% improvement in the precision by using this flex coil setup. So we'll use that for the rest of the comparison here. So first, comparing the single echo GRE to the multi-echo, we see we have a smaller off-resonance shift for the multi-echo as expected. The slightly lower duty cycle is compensated by the longer echoes of the longer echo times of the later echoes. So the precision in the two measurements are equivalent. Comparing the single echo GRE to 2D EPI, we see we can get a larger coverage, 7 slices here in the same scan time, where a smaller off-resonance shift. We do start to see some ghosting in the images, but the price we really pay for this larger coverage is a lower precision in the measurement. Comparing to a 3D approach, so now we're requiring a contiguous slab of 12 slices. In this setup, the scan time was a little bit longer, but again, smaller off-resonance shift. And again, the price you pay for that coverage is in a lower precision. So to sum up, compared to the currently used single echo, the multi-echo, you do have a smaller off-resonance shift, and there are no real disadvantages to doing that. Compared to a 2D EPI approach, you get a larger coverage with the same smaller off-resonance shift, but you pay a price in the precision. And then finally, 3D, again, larger coverage and smaller off-resonance shift. And here, like we saw earlier today, we think there is some added value that you can get a thick slab, so you can very fast and accurately localize the focal spot very accurately, and there potentially won't be any need to do these repeated 2D slices in different orientations to find the focus. And this can probably be especially useful if you're off-center, so you have oblique focal spot, as we saw in some talks yesterday, because you get the whole slab. And also if the focal spot shifts or moves during your treatment, when you titrate up the power, you'll be able to see this. And just as a 2D API, you pay a price for this coverage in the lower precision and potentially longer scan time. So that I'd just like to acknowledge our funding and take any questions.
Okay, let's open this up for questions. Do you have any questions? Any questions from the audience?
Okay, I'll ask. It's really hurt. Okay, you're losing precision on the when you go to 3D. Is there anything you can do to gain that back? What would you have to trade off there?
So I think we can optimize the protocols a little bit better. The duty cycle was quite a bit lower for the 3D. And I think the water bath is also a big problem. Because we go into the slab, we get more signal, but I think you also excite all the water in that slab. So all that noise is going to fold in. So if there's some way to kill the water signal, I think the 3D will probably help that more than it will help 2D.
Right. Okay.
Okay, thanks so much.
Thanks.